Rudewright Academy. Learn it, teach it, remember it. Today we're looking at the two ideas that make stream processing trustworthy. Exactly once. And watermarks. One protects the counting when machines die. The other decides what time really means. Let me show you both. Picture a live dashboard counting events per minute. Behind it, a pipeline chews through 400,000 events every second, spread across many machines. This afternoon, one of those machines dies mid-count. 30 seconds later, the pipeline is back, and the dashboard is still exactly right. Not one event lost, and not one counted twice. How do you rebuild a machine's memory in the middle of a stream that never stops? Forget machines for a moment, and picture yourself counting a big stack of letters. You keep a running tally in a notebook, and you keep a bookmark in the stack so you know how far you've gotten. If someone interrupts you, no problem. Open the notebook, find the bookmark, and keep counting from there. But there's a trap hiding in this routine, and it is the whole lesson. The tally and the bookmark only save you if they were written down at the same moment. If they describe two different moments, one of them is lying. Streams already know how to replay. A reader remembers its position in the log, and after a crash it rereads from the last position it saved. So nothing is ever lost. That guarantee is called at least once. Every event gets processed one time or more. And it's the or more that bites. Watch. Our counter has processed 6 events, so the true count is 6. But it saved its count after event 6 and its position after event 4. The machine dies. On restart, it loads the count 6. It rewinds to the bookmark 4. And it replays 5 and 6, counting them again. The dashboard now says 8. No error fired. The number is just quietly wrong. So here is the move everything else builds on. The count and the position must be captured together in a single photograph of one instant. State and position, one atomic pair. Restore the photograph and replay everything after it, and every event lands in the count exactly once. Events from before the photo are already inside it. Events after the photo are exactly the ones that get replayed. Nothing can straddle the line because there is only one line. But a real job is not one counter. It's a graph of operators spread across machines. Sources reading partitions. Filters. Keyed aggregators holding millions of counters. And sinks. You cannot stop the world to take a photograph, so the photograph travels. On a schedule, a coordinator injects a barrier into each source. A special marker that flows along with the data like a dye line in a river. Everything ahead of it belongs to the photo. Everything behind it does not. When an operator sees the barrier, it snapshots its own state and passes the barrier on. One subtlety. An operator with 2 inputs must wait for the barrier on both. So it pauses the channel where the barrier arrived first, lets the slower one catch up, and only then takes its snapshot. That wait is called alignment. When every operator has confirmed, the coordinator marks the checkpoint complete. Let's run the whole story once concretely. Events 1 through 4 flow through and the count reaches 4. The barrier is injected right behind event 4. The source records position 4. And when the barrier reaches the counter, it records count 4. One photograph. 4 and 4. The coordinator marks it complete. Events 5 and 6 flow on, so the live count reads 6. And then the machine dies. Now watch an update. Restore the counter to 4. Rewind the source to position 4. And replay. Now, before you look, a question. 5 and 6 are about to come through again. What will the counter read when they're done? It reads 6. 5 and 6 were the only events missing from the photograph, and they are exactly the ones the replay delivers. Exactly once, by construction. There's still one door the duplicates can walk through. The output. Suppose the pipeline wrote a result to the database after the photograph and then crashed. Replay recomputes that result and writes it again. So the guarantee has to extend into the sink. When the barrier reaches the sink pre-commits its pending results. Written but staged invisibly, stamped with the checkpoint's epoch. Say epoch 7. When the coordinator confirms the whole checkpoint, it broadcasts commit 7 and the sink flips the staged writes visible. Now walk the failure window. The job dies between the pre-commit and the commit. On replay, the sink receives the same results, stamped with the same epoch 7. It remembers epoch 7, so it accepts them without writing twice. Epochs make the handshake safe to retry. And when the sink supports upserts, there's a simpler road. Give each result a deterministic key and write it as an upsert. The same result written twice lands on the same row. Everything so far protects the counting. But which minute does an event belong to? There are two clocks. Processing time is when the event reached the engine. Event time is when it actually happened, the timestamp it carries. And they disagree constantly. A phone goes through a tunnel, comes out, and uploads a minute-old burst. Window by processing time, and that burst lands in whatever minute it happened to arrive in. The wrong one. And if you ever replay yesterday's stream, arrival shift, and the same data gives different answers. Window by event time, and every event lands in the minute it truly happened. Replays give identical answers. Event time is the correct clock. It just leaves one question. If events can arrive late, when is a window finished? The engine can never be certain a window has everything. There could always be one more straggler. So instead of certainty, it makes a measured bet. The watermark. A moving assertion that says, I believe I have seen everything older than this time. The rule is simple. Take the biggest timestamp seen so far and subtract an out-of-order allowance. Let's watch it. Our window collects second 0 to second 30, and the allowance is 15 seconds. Events arrive stamped 5, 18, 12, out of order and harmlessly so. 28, then 39. Here's a question. Biggest stamp 39, allowance 15. Where does the watermark stand? At 24. And 24 has not reached 30, so the window stays open. Then 47 arrives. The watermark moves to 32, and that crosses the end. The window fires. 4 events sealed. The allowance is the honest price of correctness. Every result waits it out. The watermark is a bet, and some events lose it. Here comes an event stamped 22. It belongs to our window. But the watermark already stands at 32, and the window has fired. You have 3 choices. Drop it and accept the loss knowingly. Keep the window state alive for a grace period and refire a corrected result. Or route it to a side output. The tombstone meets key 51 for offline repair. The one thing a serious pipeline never does is drop late data silently. Lateness is a budget you chose with the allowance. Give it an explicit home. One more behavior, and it's the one that pages you at night. Each input partition carries its own watermark, and the global watermark is the minimum of them all. The engine can only be as sure as its most uncertain input. Now one partition goes quiet, a region asleep. Its watermark freezes at 9 while its siblings march past 30. The minimum stays at 9 and no window ever fires again. Here's the cruel part. Nothing is broken. No errors, healthy graphs, and 0 output. The fix is for an Idle-Partition to say so. After a quiet interval, it emits a heartbeat. A watermark with no data, meaning nothing happened but time has passed. And the global clock is free to advance. One caution. Quiet because idle is not the same as quiet because stuck. A partition held back by back pressure still has events coming. Both guarantees have a price, and you should be able to derive it on a napkin. Checkpoint every 60 seconds at 400,000 events a second. A crash at the worst moment replays 60 times 400,000. 24 million events before fresh output flows. Shrink the interval, and you replay less, but you photograph more often. The watermark allowance is the other dial. Allow 15 seconds of disorder, and every single result arrives 15 seconds after its window truly ended. Exactly once costs you checkpoint work. Event time costs you watermark delay. A senior answer names both numbers. Put the two designs side by side and crash them identically. On the left, at least once with sloppy bookkeeping. On the right, the barrier photograph and the committed sync. The same events flow into both, and both counts read 7. Now, the same crash on both. The left restarts, replays, and double counts. The truth is 7. Its sync says 9 with a straight face. The right restores, replays into clean state, and commits on confirmation. 7 before the crash, and 7 after. Same hardware, same failure, same data. The only difference is discipline about moments. So where will you meet this? Billing and metering pipelines where a duplicate is money and a loss is an angry customer. Live operations dashboards where windowed rates decide who gets paged. Fraud detection where the pattern only makes sense on event time. And sensor fleets where devices sleep, wake, and upload the past. Out of order is the normal case there, not the exception. And in the architecture interview, 2 probes separate a memorized diagram from an understood one. How does exactly once reach the sync? And what happens when one partition goes idle? You can now answer both. So, 1 photograph, 1 promise, 1 clock, 1 bet. Replay from a saved position gives you at least once. Snapshotting state and position together, the barrier's photograph, turns replay into exactly once inside the pipeline. Committing outputs only when the checkpoint is confirmed carries the promise into the sync. Then, for time. Window by the event's own clock. Close windows on the watermark's bet. And give late events an explicit home. Snapshot together. Commit on confirm. Close on the watermark. Want to keep learning? Come find us at academy.rudewrite.com.